We're going to start with evaluating a function for different values of x. And let's just start with a very simple case where our function has a single formula, f of x is x squared plus 2. How do I evaluate f of minus 2? Well, wherever I see x in the formula, I put in minus 2. So f of minus 2 must equal minus 2 squared plus 2. So this x really acts like a placeholder for a value, and in this case my particular value is negative 2. So f of negative 2, the rest are details. Negative 2 squared is 4 plus 2, and now my value, f of negative 2, is 6. So f is a rule which sends x to x squared plus 2, and it sends negative 2 to 6. So when I feed negative 2 into this machine called f, then it spits out the value 6. What about when I put in 0 instead of x? So again, remember, x is just a placeholder for whatever number I'm going to put in here. So when x is 0, then the value of the function is x squared plus 2, that's 0 squared plus 2, and that's 0 plus 2, that's just 2. So f is this rule which, when I take the value 0, it transforms that value to 2, or it transforms that number to 2. What about f of 3 over 2? Well, again, I substitute 3 over 2 for x here, and I get f of 3 over 2 is 3 over 2 squared plus 2. Now the rest are details. That's 9 over 4 plus 2. It's 9 plus 8 over 4. That's 17 over 4. So this rule called f, when I feed it 3 over 2, it spits out 17 over 4. And again, when I feed it 10, it gives me 10 squared plus 2, and that's 100 plus 2, which is 102. Now, not all functions are as simple as f of x equals x squared plus 2. In other words, not every function can be described so compactly. And sometimes what's going on, especially in reality, has to be described with more than one sentence. And in other words, it has to be described in pieces. And functions which are described in this way, we call them piecewise defined functions for obvious reasons, because it takes perhaps a number of formulas to describe what's going on. And of course, part of the art of using piecewise defined functions is to take something in reality and translate it to an algebraic, an algebraic description of a piecewise defined function. And once you've done that, then you're free to use the theory of functions to apply that to the situation in reality. Here's a simple example. The cost of parking at South Bend Airport, it might be a little outdated right now, depends on how long you leave your car in the short-term lot. And right at the entrance to the lot, there at least was, a number of years ago, a placard saying the following. This describes the parking rates. The first 30 minutes are free. Next 30 minutes cost $2. They didn't write it this way. They said next 30 minutes is $2. Each additional hour is $2. And then there's a 24-hour maximum rate of $13. And then after 24 hours, your car gets towed, which isn't good. So how can we translate this situation to a function? Obviously, the cost of parking your car there is a function of time. And the more time your car stays in the lot, the more you're going to pay, and the greater the consequences. So we can give this function a name. The cost of parking, I can call that C. And it depends on the amount of time my car spends in the lot, so I'm going to call that T. And I'm going to measure T in hours. And now this first statement says the first 30 minutes are free. That means that for T between 0 and 1/2, I pay nothing. I pay $0. So the cost, C of T, is going to be 0 whenever T is between 0 and 1/2. So just like it was complicated to describe what's going on, required several lines, the description of this function is also complicated and requires several formulas and several lines of explanation. So this pretty much takes care of this statement, that C of T, the cost of parking my car for T minutes, is 0 if the T is between 0 and half an hour. What about if my car spends somewhere between half an hour and an hour in the lot? Well, that means that's the next 30 minutes, and that's going to cost me $2. So if T is anywhere between 0.5 and 1 hour, then I'm going to pay $2. So C of T is 2 when T is between 0.5, a half hour, and 1 hour. Well, that takes care of statement number 2. Now, every additional hour is $2 until I get to this 24-hour maximum rate, and then after that, the car is towed. So after 24 hours, the car is towed. Not good. Okay, so what about the next hour? Between 1 hour and 2 hours, if I leave my car in the lot for somewhere over an hour but less than 2 hours, I'm going to pay this $2 plus $2 more. So that's going to be $4. And then if I leave it in there for an extra hour, 2 to 3 hours, then that's going to cost me $6. So if I've left the car in the lot for some value of T, which is greater than 2 hours but less than 3 hours, I'm going to pay $6. So C of T is $6 in this particular case. If I leave the car in the lot for somewhere between 3 and 4 hours, then C of T is $8. Between 4 and 5 hours, C of T is $10. Between 5 and 6 hours, C of T is $12. And between 6, it doesn't get worse than $13. So if I leave it over 6 hours and somewhere less than 24 hours, then I'm going to pay the maximum rate, which is $13. So this says that the maximum I'm going to pay is $13. So this stops increasing after 6 hours. Okay. Then after 24 hours, they're going to tow the car, so I'm going to pay that $13 for parking plus the cost of towing. So the point is here that the cost of parking depends on how much time I leave the car in the lot. And to evaluate that cost, I have to figure out which of these time frames the time that I've left the car in the lot fits in, and then figure out how much that costs according to this complicated description. Now, there's absolutely no way to describe what's going on here in a single formula, as the people who made this placard at the airport figured out. In this case, the verbal description is a little more compact than the algebraic description. However, this detail allows us to calculate a little more quickly what the cost of parking is going to be. So if I'm trying to figure out how much I need to pay using this more detailed description, I first figure out how much time my car has spent in the lot, which of these categories it's in, and then what the corresponding value of C of t is. So we could give an abstract definition for a formula that looks like this, and when we explore piecewise defined functions, we explore formulas which are given in pieces. So here's a slightly more abstract piecewise defined function. Let's call it g of x, and g of x is x plus 1 if x is in this category, x is bigger than 1. G of x is x squared if x is between minus 1 and 1, including minus 1 and 1. And g of x is 4 if x is less than minus 1. So again, we have a piecewise description. In this case, we're given a formula for g for each of the categories of where x might be. And we can evaluate this function at any given x by figuring out which category the x lies in here. So for example, g of minus 2, what is it? Well, I have to figure out which category minus 2 is in. And minus 2 is in this category here. It's an x value which is less than minus 1. And now I see that in that case, g of minus 2 must be 4. Since minus 2 is in the category x less than minus 1. Here, x is minus 2. What about g of 0? Well, which category is 0 in? It's between minus 1 and 1 for sure. So it's in this category, and in that case, g of x equals x squared. So g of 0 is 0 squared, which is 0. Since minus 1 is less than or equal to 0, which is less than or equal to 1. What about g of 3 over 2? And again, of course, you should try to calculate these and then look at the answers later. Well, first we figure out which category 3 over 2 is in. It's bigger than 1. So g of 3 over 2 must be 3 over 2 plus 1. And that's equal to 3 plus 2 over 2, that's 5 over 2. And of course, g of 10 is bigger than 1, so g of 10 is 10 plus 1, which is 11. Pardon me, 11, not 1.